Hey everyone. After moving on to something new and powerful, namely learning how to split our program code into multiple files, for 68 lessons we've been using just a single file, main.cpp. Or maybe it had a different name, that part doesn't really matter. Starting with this lesson and moving forward, we're constantly going to create new files, and our programs will consist of many different files. But first, we need to understand why we even split code into multiple files in the first place. Why can't we just keep writing everything in one single file? When a program is small, using one file feels convenient because you can quickly look through the entire code base. But that's only because we haven't written that much code in a single file yet. In the practical C++ lessons on my channel, you've already written a lot of function prototypes, function definitions, multiple structures at the same time, and shoved all of that into one file. And that alone may have already started feeling uncomfortable. As the number of lines in a file grows, problems start appearing. Writing code becomes harder. Understanding the structure of the code becomes harder. Navigating through the code becomes harder. Maintaining the program becomes harder. Finding bugs becomes harder. Imagine a single file that contains all the rendering code, physics code, audio systems, networking, UI systems, safe systems, AI systems, inventory systems, input systems, plus gameplay logic on top of that. Even if only one person is writing all of this, it eventually turns into complete chaos. A large program can be divided into multiple subsystems. For example, if we're talking about game development again, we can place math-related functions into one file. Audio-related functions or audio entities can go into another file. UI systems or inventory systems can also be separated into their own files, which themselves can live inside folders with clear names. Imagine a game project that has an inventory system. That inventory system consists of several structures and around 20 or 30 functions, maybe even more, for working with those structures and related data. Now, let's say you want to understand how the inventory system works, or maybe you discovered a bug there that you need to fix. If everything is located inside one huge file, you'll waste a ton of time just trying to find the inventory system itself, not to mention finding the bug inside it. But if the inventory system is separated into dedicated files located inside a folder called something like inventory, then understanding the system and finding bugs becomes much faster. Let's say you're writing some program where you frequently use your own structure called matrix, or maybe you constantly use a vector structure. If everything lives in one file and the project works, you don't really think about it. But then you start creating a new program and realize you need that same matrix and vector again. At that point, you either rewrite everything from scratch, potentially introducing new bugs again, or you copy the code from the previous project. But since everything in the previous project lives inside one giant file, you now have to spend time figuring out what exactly to copy. If, however, your first project had everything properly separated into files, you could simply find a file called metrics.cpp, copy it into the new project, and immediately use it. Now let's talk about multiple programmers. Imagine a company wants to develop a project and they have 10 developers. If all of them keep writing their own version of main, it becomes complete chaos. First of all, they obviously can't all sit at the same computer and edit different parts of the same main file simultaneously. So maybe each developer has their own version of main function where they implement something and later someone, or all of them one by one, tries to merge all those versions into a single file. That's terrible. Nobody works like that. Programmers usually work either in their own separate files and subsystems, or sometimes they do work on the same file. Conflicts can happen. For example, one programmer decides to add a field to a structure while another programmer removes a field from that same structure. That creates merge conflicts, which can be resolved in different ways, but we're not talking about that today. Another issue, imagine again that you're developing a game and you decide to change a single function somewhere in your system. In that case, you only need to recompile the file that contains that function, while the other files don't need recompilation. But when everything is written in one file, any change anywhere in that file requires recompiling the entire thing. And naturally, the more code the file contains, the longer compilation takes. It's common to separate concepts like interface and implementation. If you write a function, then either you or another programmer will eventually want to call it. To call a function, you only need to know its name, parameter types, and return value. And ideally, you should also know what the function actually does. That's called the interface. More technically, we can say it's the function declaration or function prototype. Everything inside the function itself is usually called the implementation, meaning the actual code the function executes. If everything is written in one file, both the interface and implementation are visible to everyone. But if things are separated into different files, you can place the implementation in one file and the interface in another. Other programmers can then use only the interface file. Because of this, you don't change the interface, but only change the implementation. For example, you fixed a small bug inside your function that other programmers already use. You can simply update your CPP file, recompile it, and the other files won't need recompilation. Other programmers may not even realize you fixed a bug. This concept is called implementation hiding or encapsulation. We'll talk about it in much more detail later when we study object-oriented programming. So, when you work with files, you should divide your program into modules and subsystems, exactly like I mentioned earlier. If your game uses audio, it's usually best to implement it as a separate module. Same things go with physics, UI systems, artificial intelligence, and so on. The same idea applies to standard libraries. For example, you use cout all the time, but you probably don't even know what it actually is. In reality, it's a global variable of some type, and you don't even know what's inside that type. And honestly, you don't need to know. All you really need is the interface, how to use cout and what it does. In this case, it outputs information to the screen. That's it. That's why working with files is fundamentally about managing program complexity. You need to develop an intuition for when something should go into a separate file and when it's okay to keep things together. Usually, that intuition comes with practice. The more code bases and resources you study, the better you understand where different tools and systems should live. Now, let's say you listened to me and decided to start writing programs with multiple files. We have a simple task. There's a player who has a name and a health value. Inside the player's inventory, there are potions that increase health. We need to implement all of this. And we also need a function that prints the player's information to the screen. So you start thinking, okay, maybe let's create a file called inventory.cpp, where we'll write a function called addHealth. This function takes two parameters, a player passed by reference and the amount of health to add. But for the compiler to understand what player is inside this file, we need to define the player structure there containing a name field, which is an array, and a health field, which is just a number. Seems fine. Then maybe inside player.cpp we write a function called printPlayer, then that outputs the player's information to the screen. We pass the player as a const reference because we don't want to modify the player or any of their data while simply printing information, so the reference is const. But since we use cout, this file also needs to include iostream, and the function outputs the two fields of the player. The problem is that the compiler currently knows nothing about inventory.cpp or the code inside it. So here, the compiler also won't understand what player is unless we define it again. which means we duplicate the player structure definition here too, and then output its fields. Then inside main.cpp, we create a player object, print its information, add some health, and print the information again. What's the problem? First of all, if you want to use the player structure in this file, you once again need to define it here. So we repeat the structure definition again. Next, the compiler doesn't know about functions located in other files. We must declare them manually, meaning we write their prototypes or declarations here. We basically copy the function headers from other files, paste them here, and add semicolons. After that, the compiler can finally compile the code. By writing those prototypes, we're telling the compiler, hey, somewhere in this project, there will be an implementation of this function. Don't worry about it. Just compile this code for now. Later, during linking, the linker starts searching for those functions. If it can't find them, you'll get linker errors, which we'll discuss later. If it does find them, then everything works correctly. So now in main, we create our player using an initializer list. Then we call the first function, the second function, and the third function. If we run the program and everything works correctly, we should see the player's information printed twice, once before increasing health and once after increasing health. And this example contains only 3 functions and 1 structure. Yet even this tiny example already demonstrates a huge number of problems that only get worse as the amount of code grows. The first problem is code duplication. Our player structure is duplicated across 3 different files. If we decide to change one of its fields, for example, replacing int with float, we must update it in every single file, which means we also need to remember exactly which files contain that structure. Because if we forget even one place, the project won't compile. Inside main.cpp, we also have to manually write declarations for every function we want to use. What if there are 20 functions? Then we need to write 20 declarations. And what if we need those same 20 functions in several more files? Then we'll have to duplicate those declarations again and again and again. We can also make mistakes in those declarations. For example, in the prototype for add health, we might accidentally write an int parameter, while the actual implementation inside inventory.cpp uses a float parameter. In that case, the linker will fail to find the correct function and throw an error. The fourth problem is that the project has no centralized interface. Nobody knows which functions or structures exist or what interfaces are available without opening multiple files and searching manually. And the real disaster begins once the number of structures and functions keeps growing. The more structures you create, the more times you'll have to duplicate their definitions across different files. Same thing with functions. You end up duplicating a massive amount of entities. So what do? And this is where header files come into play. A header file is a file that usually contains declarations of your entities, interfaces, or type definitions, and it's designed for sharing code between different source files. So here's the deal. In C++, code files are generally split into 2 categories, source files and header files. Source files usually have the .cpp extension. Header files can have different extensions like .hpp, .h, and others, but .h is the most common one. It simply stands for header. Up until now, we've only been writing source files. Even in the Solution Explorer, on the right side, we created them inside the source files section. And technically, that's not even a real folder, it's just a filter, because the actual folder doesn't physically exist on disk. It only exists inside Solution Explorer as a visual grouping. So we'll call it a filter. Basically, a fake visual folder. Above it, you can also see the header files filter. That's where we can place our header files. A header file usually describes what exists, while a source file usually contains how it works. Although before I show you the implementation, I want to make one thing clear. Technically, you can write absolutely everything inside header files that you can write inside CPP files. There's nothing stopping you, but there are certain conventions and best practices for writing header files. And if you ignore them, then using header files becomes pretty much pointless. So let's create a header file. Just like when creating a .cpp file, we right-click the filter, choose Add, then New Item. A window opens, and the second option is header file, where Visual Studio automatically gives it the .h extension. Let's call our header file player. You may notice that after creating it, the file gets a different icon compared to source files. That's how you can visually distinguish header files from source files inside Solution Explorer. You might also notice that Visual Studio automatically generated some code inside the file. We'll delete it for now, but we'll discuss it later in this lesson. Now let's try restructuring our program using header files. First, we can move our structure into a header file. So we go through all our files and copy the structure into the header file. Second, everything related to the player, specifically the print player function, should also go into the header file. But notice, we copy only the function declaration and not the implementation itself. I'll explain why later. For example, we can go into inventory.cpp, remove the structure definition from there, and instead include our file called player.h. Notice that I'm using double quotes instead of angle brackets because this is a project file, not a standard library file. And back in the lesson about preprocessor directives, I told you that the include directive simply takes everything inside the file and pastes it into the current location. So in this case, the directive literally inserts all this code here for us. Next, we go into player.cpp. Same thing there. We remove the structure definition and add a directive that includes player.h. Then inside main CPP, we remove everything that we already placed into player.h and include that header instead. Now, the @health function belongs to the inventory system, so it shouldn't live inside main. It should have its own file. So let's create another header file called inventory.h. We place the function declaration there, and immediately we get a compilation error because the compiler doesn't know what player is. To fix that, we simply include player.h inside inventory.h. Now the compiler understands everything. After that, inside main, we can remove the @health prototype and instead include inventory.h. And just like that, we solved all our problems. Why? Because now we have two header files and two source files. All function implementations live inside source files. Inventory.cpp contains the implementation or definition of @health, while player.cpp contains the definition of print player. If we want to use these functions in other files, we simply include player.h or inventory.h. Same thing with the player structure. Its definition now exists only inside player.h. So if we want to change its fields or add new ones, we do it in exactly one place. We no longer duplicate it everywhere. If you still don't fully feel the benefits of header files because our project is tiny, that's completely normal. But imagine that inventory.h contains a structure called potion with fields like health amount, potion name, potion color, and so on. Then imagine several functions related to potions: drain potion, empty potion, update potion, create potion. Then maybe you also have structures like inventory or backpack, each with their own functions. Now imagine that inventory.h contains 10 inventory-related structures and 40 functions. And I want to use all of that inside main. To do that, I only need to write one line: include inventory.h. If my inventory system changes internally, the code inside main doesn't need to change because we still include the same single line. Now imagine we create another file called render.cpp where we write rendering-related functions. Maybe we want to display the inventory on the screen. That means we need access to inventory tools and functions. And again, to use the entire inventory system there, we only need one line, include inventory.h. So using header files in your projects helps you avoid duplicating structures, duplicating structure definitions, duplicating function declarations, helps prevent mismatched function signatures, solves the problem of not having a centralized interface, and greatly improves your project's scalability. What does scalability mean in this context? It means that if you want to add new functionality, for example, new inventory features, you shouldn't need to modify other files across the project. You simply go into the inventory files and add the new functionality there. What should actually go inside a header file? Short answer, a header file, or simply header, should describe the interface, not drag in unnecessary implementation details or dependencies. Nowadays, pretty much all experienced programmers recommend placing the following things inside header files. Let's switch over to the second project where I created a header file called GoodHeader and take a look at its implementation. The first thing you should place inside a header file is function declarations. We do this to provide an interface to other files. Other files should not need to know what the actual function definition looks like. They only need to know what the interface looks like. If instead of a declaration, you place a full function definition inside the header, meaning the function header together with its code body, and then include that header in two different files, you'll get a compilation error because the function ends up being defined in two places. And how is the compiler supposed to know which definition to choose? It doesn't choose, it simply throws an error. Remember how up until now we wrote function prototypes before main and then placed the actual function definitions after main? I told you back then that this was preparing you for separating interface from implementation. And now we finally reached that point. All those prototypes you used to write above main should now go into header files. And all that actual function definitions you used to place below main should now go into the corresponding source files. The next thing commonly placed into header files is definitions of classes and structures. You don't know what classes are yet. In about 10 lessons or so we'll get there, but you already know what structures are. You already saw in the first project that if you want to use a structure across multiple files, you'd otherwise need to redefine it everywhere. To avoid that duplication, you define it once inside a header file and simply include that header wherever needed. Exactly the same logic applies to classes. A class is also a data type, just like a structure. There are some small differences, but for now, think of them as basically the same thing. You can create variables of them, arrays of them, and so on. And they have exact same problem as structures. If you don't centralize their definition, you end up duplicating them everywhere. So class and struct definitions belong in header files. The same idea applies to other user-defined types such as enumerations and unions. All user-defined type definitions should generally live in header files. Otherwise, you'd constantly duplicate those type definitions across multiple files. Another thing commonly placed into header files is templates. More specifically, template definitions. You don't know templates yet, but we'll cover them in a future lesson. Very roughly speaking, templates are instructions for the compiler to generate functions or classes that work with different data types. Right now, that may sound confusing or impossible to understand, and that's completely normal. For now, just remember this. If you see the keyword template, you're dealing with some kind of template. For example, here we have a function called max. It takes two parameters, compares them, and returns the larger one. This is a template function. And notice, instead of only writing its declaration, we actually write the full definition. Why? I'll explain that in the templates lesson. Next, inline functions. We already had a lesson about inline functions. These are functions where the compiler may insert the function's code directly at the call site instead of jumping to the function's address and executing it normally. So it's basically a small optimization. And as you remember, an inline is only a request to the compiler. The compiler still decides on its own whether to inline the function or not according to its internal rules. If a function is very small, you can mark it inline and maybe the compiler will inline it. Although modern compilers are already pretty good at automatically deciding which functions should be inline, so the keyword itself is a bit outdated nowadays. Now you might ask, why the hell are inline function definitions allowed inside header files while regular function definitions aren't? Because the compiler explicitly allows it. If you include a header containing an inline function in multiple files, you won't get an error. In other words, your project is allowed to contain multiple identical copies of an inline function definition. The important part is that all those copies must be identical. Next, const eval function definitions. You don't know what those are yet, so we'll skip the details for now. When we eventually cover these keywords in dedicated lessons like const expr and const eval, I'll remind you about this. Very briefly, const expr functions can be evaluated at compile time, and const eval functions must be evaluated at compile time, and their definitions are usually placed inside header files. Another thing you can place inside headers is variable definitions with the inline keyword. You don't know this feature yet either, but we'll discuss it later in this lesson. If it's just a normal variable without inline, then defining it inside a header is illegal because that creates multiple definitions of the same variable once the header gets included in several files. But if you add the inline keyword, everything becomes fine. By the way, this feature was added in C++ 17. Another perfectly normal thing to place inside header files is includes of other header files. For example, if we look at iostream, the file we constantly include, you should know that it's also a header file. Standard library headers in C++ simply usually don't have visible extensions. And if we open iostream internally, we'll see that it itself includes many other header files. A header file can include as many other headers as necessary. It's also common practice to place type aliases inside header files, either aliases created with using or aliases creating with typedef. Another thing commonly placed into headers is concepts. We'll talk about concepts in a separate lesson far into the future, assuming I survive long enough to make the lesson. Concepts are a fairly new feature introduced in C++ 20. They're powerful and convenient, although somewhat specialized. Now let me give you an important recommendation. Even though you can include as many headers as you want, always include only what you actually need. For example, in this file, I only need std vector and std string, so I included only those two headers and nothing else. Because if you include tons of unnecessary headers, the amount of code being processed grows dramatically. And if your header gets included into many source files, then all of those files become larger too. That increases compilation time, increases the size of object files, and eventually increases the size of the final executable as well. So if you want faster compilation and smaller binaries, include only the headers you truly need. Next comes an interesting topic, forward declarations. You already know how to declare functions. You simply write their signature followed by a semicolon and amid the body. You also know how to declare variables. You write the extern keyword followed by the variable type and name, but without a value. Well, you can do the same thing with types. To do this, you write the keyword associated with the type, for example, class, struct, enum, or union, followed by the type name and a semicolon. That's called a forward declaration. Why it exists and why it matters, I'll explain later in this lesson. Now, let's separately talk about declarations of global variables. I already explained what global variables are. variables accessible from any CPP file. But for another CPP file to access such a variable, that variable must first be declared there. Imagine our first project with 3 files. Suppose the global variable is defined inside player.cpp, but we also want to use it inside main.cpp and inventory.cpp. Then in both of those files, we need to write a declaration for that variable. We do that using the extern keyword followed by the variable type and name, but without a value. Because if you provide a value, extern gets ignored and the statement becomes the definition instead. And we are not allowed to create multiple definitions of the same global variable across our files. So if you want a global variable defined in one file to be usable from other files, you can place its extern declaration inside a header file. Although modern programming generally discourages using global variables to get all together. Why? Because in large projects, it becomes extremely difficult to predict their current values. Any file can modify them at any time. You might be working inside one file expecting the variable to contain a specific value, while somewhere else another file already changed it behind your back. You may also encounter macros inside header files. Macros can exist in CPP files too, but they appear more frequently in headers. However, modern CPP tries to avoid macros whenever possible and instead prefers global expr constants, meaning constants evaluated at compile time. And speaking of constants, defining constants inside header files is actually perfectly normal. Why? Let me explain. When I talked about the static keyword earlier, I probably already explained this concept. In C++, we have something called linkage. More specifically, no linkage, internal linkage, external linkage. When you create a data inside a function, it has no linkage. It exists only locally inside that function. When you create a function or variable outside functions, it has external linkage by default. That means it can potentially be accessed from other files. Then there's internal linkage. That means the variable or function is visible only inside the current file. To achieve that, you add the static keyword before the variable or function. And because of that, static functions and variables are generally not recommended inside header files. So why are constants okay? Because const variables have internal linkage by default. In other words, it's almost as if static is automatically applied to them. That means when you include a header containing a const variable into multiple files, each file gets its own independent copy of that constant with internal linkage. And because of that, no multiple definition errors occur. By the way, cout is actually a global variable. Even though programmers generally discourage creating global variables, both cout and cin are global variables. There's your fun fact for today. And honestly, that's enough for this list. So in the future, whenever you ask yourself, should I move this into a header file or not? You can come back to this section of the lesson and answer that question yourself. Now let's look at a full proper example of using header files. Let's switch over to the third project. Inside main.cpp, I already laid out the structure of our project. We have a simple program whose job is to measure temperature and store it somewhere. Let's say we have 3 places where temperature needs to be measured: our room, outside, and the server room. The entity responsible for measuring temperature will be called sensor. So I'm going to create 2 files for it, a header file and a source file. Everything related to the sensor will live there. Next, we'll have a weather station that stores those sensors internally. Since that's its own separate entity with its own functionality, I'll also place it into its own pair of files. And finally, we'll need a bunch of functions for printing various pieces of information related to the station and sensor temperatures. So I created another pair of files specifically for output and reporting functionality. Also, in real projects, you often have utility functions or helper tools shared across multiple systems. Things like random number generators, min-max functions, clamp functions, and so on. I placed those into another dedicated module. So let's first analyze our header files. We'll start with sensor.h. Inside it, we have a structure called temperature sensor. It contains the following fields: the sensor name, current temperature, minimum and maximum recorded temperatures, and a variable indicating whether the sensor is currently active. Below that, we have prototypes for functions that work with our sensors. Now, let's immediately switch to sensor.cpp and analyze those functions. Here we can see that I include two files. First, IOStream. Second, our own header file. I include IOStream because I use cout in this file. And I include sensor.h so the compiler understands what temperature sensor looks like inside this file. And also, so we don't accidentally make mistakes when writing function template headers. Here we have the create sensor function. It takes a sensor by reference and the name we want to assign to that sensor. Then we create a variable called I. Using this loop, we copy the name from the parameter into the sensor internal name field. And at the end, we explicitly place the null terminator so the character array becomes a proper C-style string. Then we initialize the sensor with default values. After that comes the setTemperature function. It takes the sensor by referencing and the new temperature we want to assign. We update the current temperature and then check whether the new value falls outside the existing range. If the new temperature is lower than the minimum recorded temperature, we override the minimum value. If it's higher than the maximum recorded temperature, we override the maximum value as well. The next function prints the sensor's name and the current temperature to the screen. So next function simply returns the value of the sensor's active field. You might ask, why even create a function for that? Because a well-named function often communicates intent better than directly accessing the variable itself. Also notice that here we pass the sensor by const reference because we do not modify it. If your function doesn't modify structured fields, you should protect that parameter with the const keyword. There's also a function that returns the sensor's temperature range, basically the difference between the maximum and minimum recorded temperatures. Now let's move on to weather.h, where our weather station lives. We include sensor.h because each station internally stores 5 sensors. There's also a sensor counter, so we can properly iterate through the sensors using loops. And there are several function declarations. Now let's switch to weather.cpp to see the implementation. Again, we include IOStream because we use cout here. And we include our own header file for the same reason as before. So the compiler understands what weather station is, and so we don't accidentally mismatch our function signatures. We have a function called addSensor. It takes the station by reference because we modify its fields, and also takes a const reference to the sensor being inserted into the station. First, we check whether the station is already full. If it is, we simply exit the program and don't add the new sensor. Otherwise, we insert the sensor into the station using the current index. Sensor count represents how many sensors have already been inserted into the station. Initially it's 0, then 1, and so on. By the way, this variable name isn't ideal because count already means quantity. A clearer name would have been something like inserted sensor count. That would communicate intent better. Next, we see the calculate average temperature function. If there are no sensors at all, we simply return 0. Otherwise, we use a standard summation algorithm, create a variable called total, initialize to 0, iterate through all sensors, and add each sensor's temperature to total. At the end, we calculate the average. We divide the total sum by the number of sensors. There's also a function called find hottest sensor. It takes the station by regular reference and returns a pointer to a sensor. Even though this function itself doesn't modify the station, I intentionally did not mark the parameter const. Why? Because what if we want to find the hottest sensor and then modify its value afterward? To allow that, we must return a pointer to a non-const sensor. If we added const here, we'd run into an error because we'd be taking a non-const station, but returning a pointer to data treated as const. That breaks const correctness, and it's generally not a good idea. Usually programmers implement two versions of such functions. One version returning a regular sensor pointer, another version taking a const station reference and returning a pointer to a const sensor. But for now, one version is enough. So first, we check whether the station contains any sensors at all. If not, we return a null pointer. Otherwise, we use a standard maximum search algorithm. We initially assume that the first sensor is the hottest one. Then we iterate through all the remaining sensors and compare their temperatures. If another sensor has a higher temperature, we update the index of the hottest sensor. After the loop finishes, we return the address of the hottest sensor in the station. Next, we move to report.h. This file is responsible for outputting information about the station. Notice that I include weather.h because this file needs to know what weather station is. By looking at the function names, we can already understand what this module does. It prints the average station temperature, prints information about the hottest sensor, and prints warnings if any sensor exceeds a specified limit. Now let's look at the implementation. Again, I include IOStream first, followed by my own header file. Notice that it's common convention to include standard library headers first, the ones using angle brackets, and project headers afterward, the ones using double quotes. That's a standard practice and a good habit to follow. We can see that print average temperature simply outputs the text average temperature along with the value returned by the function we already know. Then there's print hottest sensor. It searches for the hottest sensor pointer. If no sensor exists, it prints nothing. If a sensor is found, it prints the sensor's name through the pointer. Finally, there's print temperature warnings. It iterates through all sensors or skips the loop entirely if there are none. Then it checks whether any sensor's temperature exceeds the specified limit. If so, it prints a warning message saying that a particular sensor exceeded the limit. Now, let's move on to utility.h. This file contains generic helpful functions, a function for finding the minimum of two values, a function for finding the maximum, and a clamp function that restricts values to a specified range. Now, let's open utility.cpp and see how they're implemented. I probably don't need to explain how min and max work, but let's talk about clamp. Imagine we have a range from 0 to 10, but our value is 20. I want to clamp that value so it doesn't go outside the valid range. So if the value is smaller than minimum, we return the minimum. If the value is larger than the maximum, we return the maximum. Otherwise, the value is already inside the range, so we simply return it unchanged. Now that we've analyzed all the files, we can finally move to main CPP. What do we see here? Inside main CPP, I only include report.h. Why? Because report.h already includes weather.h and weather and sensor.h. That's already inside weather.h. So all the tools we need are already available through report.h. Now, I personally know that because I wrote the code. But in larger projects, things become much more complicated when you don't know the entire dependency chain. We'll discuss how to handle that a bit later. Anyway, all the code is available now. And by the way, IOStream also gets included through those headers, meaning we can use cout directly inside main if we want. So what do? We create three sensors. We assign them names. We assign them temperatures. Then we create a station. After that, we add all three sensors to the station. Then we print information about the entire station, the average station temperature, the hottest sensor, and whether any sensor exceeded a specified limit. Notice that I initialized the station using brace initialization. If you don't do that, sensor count will contain garbage data. Alternatively, you could assign a default value directly inside the structure definition if you don't want to initialize the station manually. Now, let's run the program and look at the output. We can see that the station contains 3 sensors. We can also see their temperatures. We see the average temperature. The hottest sensor is the server room sensor, and it's also the one that exceeded the limit. In the practical lesson about header files, you'll get many more interesting exercises involving real usage of header files. But for now, let's continue with the theory. We need to take another more precise look at the concept of a translation unit. A translation unit is the result of pre-processing a single .cpp file before compilation. So imagine you have a file called weather.cpp. When compilation starts, the preprocessor begins performing all the steps we discussed back in the lesson about the preprocessor. For example, every include directive gets replaced with the actual contents of the included file. All macros get expanded and macro names get replaced with their corresponding values. After all of that happens, the original .cpp file turns into a translation unit. Header files by themselves are not translation units because they're usually included into other files, either into other header files that eventually get included into CPP files or directly into CPP files themselves. So after a pre-processing, your project still effectively consists only of CPP files, just expanded ones. And those fully processed CPP files are what we call translation units. Now, why is it called translation? Because the compiler translates a source code into object code. If you remember the second CPP C++ lesson where I talked about object files, those object files are the result of compilation, and each one is generated from a translation unit. In other words, after compilation, the translation unit becomes machine-level instructions the computer understands. Now, why is it called a unit? Because it's one independent unit of compilation. It's independent because while compiling one file, the compiler doesn't look at other CPP files and doesn't know what's inside them. It simply doesn't care. That means every single .cpp file independently produces its own translation unit after pre-processing. Then the compiler turns each translation unit into an object file. And finally, the linker combines all those object files into either an executable file or a library file. Now let's go back to why I commented out those header includes earlier. Why would I even want to include them separately? Well, imagine that inside main we first want to work directly with the temperature sensor structure and its functions. So we include sensor.h, and here we use those functions directly. Then we want to create a weather station, so we include weather.h because that's where the weather station structure and related functions are defined. And after that, we want to print all the information using the functions located inside report.h, so we include that too. We should not be required to know that report.h internally includes weather.h and weather.h internally includes sensor.h. That's bad design. So naturally, we try to include all the headers we directly use. But if we now try compiling the project, we'll get several compilation errors. Among those errors is the one we care about most, type redefinition. Here's what happens. When we include sensor.h directly into this file, the definition of the temperature sensor structure gets inserted. But then we also include weather.h, which itself already includes sensor.h. So now the temperature sensor definition gets inserted a second time, and that creates two definitions of the same structure. That's the first error. The second error happens with weather station. When we include weather.h directly, the weather station definition appears once, but then we include report.h, which itself includes weather.h, so now weather station also gets defined a second time. And there's your second error. So now we have two bad options. Either manually remember which header already include other headers, or use a technique called header guards. And obviously, header guards are the correct solution. So how do they work? Using preprocessor directives and macros, we can check whether a header file has already been included before. If it was already included once, we simply skip it the next time. Here's what that looks like. Let's open sensor.h and at the very top write if and def some macro. Then we define that macro. And after that, we place the entire contents of the file inside this block. Technically, that alone is enough to protect the file. Now, let's see how it works. Suppose inside main.cpp we include sensor.h twice. The first time the file gets included, all the code from sensor.h gets inserted. Let's imagine that code gets pasted directly into main.cpp. What happens? The macro doesn't exist yet, so the condition succeeds. Then the macro gets defined and all the file contents get inserted normally. Now, the second time the same header gets included, the if and def condition becomes false because the macro was already defined earlier. And because of that, everything inside the block gets skipped. So the header contents are inserted only once. And now we can apply the exact same protection to every header file. But first, let's rename the macro to something more meaningful. Usually these macros are named after the header file itself. For example, for sensor.h, we might use sensor_h, typically written in uppercase because macros are conventionally written in all caps. We can do the same thing inside report.h by creating an if and def block with a macro like report_h, and we should do the same thing for weather.h and utility.h and every other header file. Once we do that, all our header files become protected against multiple inclusion. And now inside main.cpp we can safely include all of them directly without worrying about which headers include which other headers internally. So from this point forward, whenever you create a header file, always add header guards. By the way, every standard library header we've included so far also uses this exact protection mechanism. For example, if we open the IOStream header internally, the very first thing we'll see is a header guard. It checks whether a specific macro is already defined. If it isn't, the macro gets defined and the entire file contents are placed inside that protected block. And if we open the headers included by IOStream, we'll see the same thing there too. And inside the headers included by those headers, same thing again. This protection exists everywhere. It's standard practice in C++ projects. But there's a more modern and simplified way to protect your header files using the pragma once directive. You already know that the pragma directive itself is not officially part of the C++ standard. That means everything written after pragma is compiler-specific functionality. Different compilers may support different pragma directives. However, most modern compilers support pragma once. And this directive basically replaces traditional header guards. In other words, instead of writing all those if and def, define, and if lines, you can simply place pragma once at the top of the file, and that's it. So why is pragma once better than the classic header guard we just discussed? First of all, it's one line instead of three. Second, you no longer have to come up with a unique macro name yourself, because imagine that later you decide to rename your header file. Then you also have to remember to rename the macro inside the file, and it's very easy to forget that. That's why when you create a new header file in Visual Studio, it automatically inserts pragma once by default. Personally, I use this directive everywhere, and I'll continue using it throughout this course. I use it in my own projects, and I've seen it used in tons of other projects as well. So you can absolutely start using it too. Just don't forget that the traditional header guard approach still exists and is also completely valid. Now let's move on to project number 4 and look at some common mistakes beginners make when writing and using header files. The first mistake is writing function definitions inside header files instead of declarations. If you include such a header in more than one CPP file, you'll get a compilation or linker error because multiple definitions of the same function will exist simultaneously, and that's not allowed. You'll usually see a linker error mentioning the function name along with something like already defined. Very often, you'll also see an error like one or more multiply defined symbols found. That basically means the compiler or linker found multiple definitions of the same entity somewhere in your project. The second mistake is defining global variables inside header files. If you include such a header into two source files, you'll get essentially the same error, except this time instead of a function name, you'll see the name of your variable, because, once again, multiple translation units are not allowed to contain multiple definitions of the same global entity. The third mistake is using the include directive to include CPP files instead of header files. You need to understand that include is not limited to header files only. Technically, it can include any file of any extension, .txt, .cpp, and literally anything else. As long as the file contains text, the preprocessor will simply copy and paste that text into the current file. So yes, technically you can include one CPP file into another CPP file, but you absolutely should not do that, because it almost always breaks the C++ compilation model. Here's the problem. Imagine you have two files. In one file, there's a function called sum that adds two numbers and returns the result. And now you decide to include that CPP file directly into main CPP to use the function. At first glance, this might seem convenient because no header files, no prototypes, and no declarations. Because the function definition itself gets pasted directly into main.cpp automatically. But here's the issue. Every .cpp file is compiled as its own separate translation unit. That means, first, the compiler compiles math.cpp where the sum function already exists. Then, later, it compiles main.cpp where the exact same function definition appears again because of the include. And now, you have two definitions of the same function, which results in the exact multiple definition error we discussed earlier, so never include CPP files. The fourth mistake is one we already talked about earlier, failing to protect your header files against multiple inclusion. In other words, not using header guards. You already know two different ways to solve this problem, so please don't forget to always protect your headers. The next issue is circular includes. This happens when two header files include each other, and you might ask, why would anyone even do that? Let's switch over to project number 5. Imagine we have two files. In the first file, we create a structure called weapon. A weapon usually belongs to someone, right? So we decide that inside the structure, there should be either a referenced or pointer to a player. In this example, let's simply store a player field directly. Naturally, for the compiler to understand what player is, we include player.h. Now, inside player.h, we create a player structure, and the player should probably own a weapon. Now, yes, this is a bad architecture, and you generally shouldn't design a system like this. But similar situations do happen in real projects. For example, imagine you create one class representing temperature in Fahrenheit, and another class representing temperature in Celsius. Both classes may contain conversion functions that convert one temperature type into the other, which means both entities need to know about each other, and that requires both headers to somehow reference each other. Same situation here. We have a weapon structure and a player structure. Both need to know about each other, so both headers end up including each other. Now imagine that inside main.cpp we want to create a weapon, create a player, assign the weapon to the player, and so on. The exact code doesn't matter. The important part is the include logic, because now the project won't compile. Why? Let's mentally simulate what the preprocessor does. First, we include weapon.h, so the entire contents of weapon.h get passed into the file. But then we notice that weapon.h itself includes player.h. Okay, so now we also passed in the contents of player.h, but inside player.h we see another include of weapon.h, which again includes player.h, which again includes weapon.h, and now we've created infinite recursive inclusion. So how do we solve this? We solve it using something called a forward declaration. A forward declaration is a declaration of a data type. You already know that we can declare functions. To do that, we write a function header, add a semicolon, and that's it. You also know that we can declare variables, arrays, constants, references, and pointers. For that, we usually use the extern keyword. But we can also declare types. In other words, we can tell the compiler, hey, there's a type with this name. You don't need to know what's inside it yet. You'll figure that out later. To create a forward declaration, you first write the keyword describing the type, class, struct, union, or enum, and then the name of the type itself. Now let's go back to weapon.h. Instead of including player.h, we can simply write class player. But then you'll notice an important detail. If you're inside a file where you create an actual variable of some type, then the compiler must know the full internal structure of that type. However, if you use a pointer or a reference, then the compiler doesn't need to know what's inside the type. Why? Because a pointer is just an address. The compiler already fully understands how pointers work internally. So here, the compiler simply remembers, okay, player is some kind of type. And then it allows us to create a pointer to it. Now, when we switch to player.h, things are different. Here we actually create a weapon object directly, not a pointer and not a reference. That means the compiler must know the full definition of weapon here. So in this case, a forward declaration alone is not enough. Now, if we compile the project, everything works correctly. Let's mentally simulate what the preprocessor does. First, we include weapon.h, so this code appears. Then we include player.h, and this code appears. Now look carefully at the order. First we tell the compiler, there will be a type called player, remember that. Then later we fully define player. And afterward, we define a structure that referenced it earlier. That's why everything works. If you're still new to programming and are planning to write your own classes soon, there's a very good chance you'll eventually run into circular include problems. And when that happens, just remember, okay, somewhere here I probably need a forward declaration. So how do you decide when to include a header and when to use a forward declaration? The rule is actually very simple. If your file creates an actual object of some type, meaning a variable, a constant, an array, or embedded data of that type, then you must include the full header because the compiler needs the complete definition. But if your file only contains a pointer to the type or a reference to the type and never creates the actual object itself, then a forward declaration is enough. And not only is it enough, it's usually recommended. Now let's look at another example. Maybe this one will make forward declarations feel more intuitive. Let's switch to project number 6. Here I have a file called shape.h. Inside it, we see a shape structure containing coordinates, width, and height. So this is probably some object we want to render on the screen. Now let's open renderer.h. Here we can see that this file includes shape.h. Then we define some colors, red, green, and blue. We also have a structure representing render settings, what color the shape should be, and whether the shape should be filled. And there is a function called drawShape. It takes a shape by const reference and render settings by const reference as well. We won't even look at the implementation yet. Just let's jump straight to main.cpp. Here we include 2 header files. Why 2? Because first I decided to create several shapes, and I understand that to create shape objects I need shape.h. Then later I decide to render them. For that I include renderer.h and call drawShape. I create a square. I create a circle. Well, technically it's not actually a circle, but let's pretend. Then we draw them. The square is red and filled, the circle is green and hollow. If we run the program, it compiles successfully. Of course, nothing gets printed because drawShape itself doesn't output anything yet. But the important thing here is understanding forward declarations. What's the problem in this design? The problem is that renderer.h includes the entire shape.h file. But inside renderer.h, we only use shape through a reference. And because of that, we actually don't need the full definition here. Instead of including the entire file, we can simply forward declare shape. Then we can include shape.h later inside renderer.cpp because that's where we actually access the internal fields of shape. That's where the compiler truly needs the full definition. So, what benefits does this approach give us? First, fewer dependencies. Render.h no longer directly depends on shape.h, which means that if you later modify something inside shape, render.h itself no longer needs recompilation. Second, compilation becomes faster because now shape.h no longer heavily impacts render.h. Forward declarations make headers lighter, cleaner, and more modular. So once again, if you use a forward declaration instead of including a full header, do it. When should you use it? When you only have a pointer to a type or a reference to a type. When do you need the actual header? When you create variables, constants, arrays, or embedded objects of that type. One more important note. You should not write forward declarations for types from the std namespace, but since we haven't learned namespaces yet, we'll leave that topic for later. Now let's move on to project number 7 and talk about inline variables. Starting with C++17, you can add the inline keyword not only to functions but also to data. Inside the header file, I created several global entities: a global variable, global constant, global inline variable, and a global inline constant. Now, if I comment out everything except the regular global variable, then you already know what happens. If we include that header into two different CPP files, we'll get an error because the variable ends up being defined twice. But when we create a global constant and include it into multiple files, everything works correctly. Why? Because constants have internal linkage by default. In other words, it's almost as if the static keyword is implicitly added automatically. That limits the visibility of the constant to the current translation unit. But there's still a problem. If we include that header into two different files, then each file will contain its own separate copy of the constant. That means memory is allocated for two identical constants instead of one shared constant. For tiny constants, this usually isn't a big deal, but imagine a huge object that consumes a lot of memory, and imagine including that header into 5 files or 10 files or even more. Now, every translation unit gets its own separate copy of the data, which means we're wasting memory through duplication. And there's really no reason for that duplication. That's exactly why C++17 introduced inline variables. Now, you can place the inline keyword before global data. So how does it work for variables? First of all, the project compiles successfully even when the variable is defined inside a header included by multiple files. And second, that variable becomes one single shared variable across the entire project. Every file accesses the exact same object in memory. Conceptually, this is very similar to defining the variable in one CPP file, declaring it in a header using extern, and then including that header everywhere. Except now, the syntax is much simpler, and the same thing works for constants. You can create inline constants. In that case, instead of creating multiple copies across translation units, the entire project shares one single constant object. So inline variables and inline constants can help reduce unnecessary memory duplication across your project. We also need to talk about one more term that has been surrounding everything we've discussed so far. That term is the one definition rule, or ODR. The one definition rule is a rule in C++ that says certain entities in a program must have exactly one definition. In simpler terms, you generally cannot create multiple identical definitions of the same entity inside a program unless the language explicitly allows it. ODR is one of the fundamental rules of C++. It's already connected to translation units, the linker, header files, templates, global variables, and many other parts of the language. So you absolutely need to understand the difference between a declaration and a definition. You already know that we can declare data, declare functions, and even declare types. And similarly, we can also define them. According to ODR, every function must have one definition. Every piece of data must have one definition, but declarations can appear many times. For example, you cannot define the same global variable in two different types, two different files. But you can define the same constant in multiple files because constants have internal linkage by default. Same thing with functions. You cannot define the same regular function in two different files. You define it once in a single source file, and And everywhere else, you use declarations. Exceptions are static functions. Now, and inline functions. Now, types are a bit different. You are allowed to have multiple definitions of structures, classes, enums, and similar types across different translation units. Although, in practice, the easiest and cleanest way to handle that is by defining them once inside header files. There are also exceptions to ODR, for example, inline functions. An inline function is allowed to have multiple identical definitions across different translation units. And honestly, we've already been talking about this throughout the entire lesson. Now you simply know that all of this falls under a formal rule called the one definition rule, ODR. Now let's move on to the 8th project in today's solution and compare two things. Since the very beginning of C++, the language has used header files, but in C++ 20, modules were introduced as a replacement for header files, and over time, header files are expected to slowly fade away. So what's actually wrong with header files? The problem is that the preprocessor simply copies text. That's all it does. For example, imagine we have a CPP file and some file like math.h that stores mathematical functions. When we include that header into our CPP file, the compiler literally copies the contents of the header directly into the file. Then we can include that same header into many other files, and all of them will contain identical declarations. But why are we even duplicating those declarations and increasing the size of all those files? Because all of that duplicated code still needs to be compiled. And this becomes a serious issue in large projects. Header files may end up being included thousands of times. The same code gets copied again and again and again. And the compiler repeatedly parses and recompiles the exact same content. As a result, compilation becomes slower, dependencies between files become huge, include hierarchies become extremely complicated, circular includes appear, and sometimes macros create complete chaos. And this is exactly where modules come in. Modules don't work through text copying. A module is still a file containing code, but when you use a module in another file, you don't write include anymore, you write import. And instead of copying text, the compiler precompiles the module once and then simply uses its interface. That's the biggest advantage of modules, massively faster compilation. Because a module gets compiled only once instead of thousands of times like a header file. The second big advantage is that modules do not require include guards, because the module isn't repeatedly copied into other files. The third advantage is cleaner dependency management. With header files, it's very common to end up with situations like file A includes file B includes file C includes file D. And suddenly your project becomes a giant spider web of includes. Modules make dependencies cleaner, simpler, and easier to understand. The fourth advantage is that macros become far less dangerous. With traditional headers, macros can leak into other files. For example, imagine you create a macro called max equal to 100. Suddenly, that macro may break completely unrelated code where max is supposed to be a function name. Modules isolate code much better from one another. Now, here's the interesting part. Even though C++ 20 came out around 6 years ago, most developers still use header files instead of modules. Why? Because virtually all legacy C++ code written before C++ 20 used headers. Millions of libraries still rely on header files, and tooling and ecosystem support are still evolving. So what do you actually need to know right now? Simply this. C++ now has modules introduced in C++ 20. At some point in the future, I'll make a dedicated lesson about them. But until then, we'll continue using header files so you become extremely comfortable with them. Once I eventually show you how modules work properly, I personally recommend using them everywhere possible. For now, just understand that modules are meant to replace header files in the future. And that's the direction modern C++ is moving toward. So, for example, the standard library already provides an std module. So instead of including IO stream, you can import std. You don't know how to do that yet, and honestly, it's still not entirely straightforward, but we'll discuss it in another lesson. Now, let's look at a small example. I have a header file called math.h. Inside it, we have a vector structure and a function prototype that calculates the vector length. Now, let's switch to math.cpp. Here we include our header file and also include cmath from the standard library because we need the square root function, the sqrt. We pass this expression into square root because the length of a vector is a square root of this formula. Now, if we move to main CPP, we include IOStream so we can use cout and our math.h header. We create a vector and print its length. If we run the program, we get our number. Now let's see how the exact same thing looks using modules. We create a module file. In Visual Studio, you can choose something like C++ module interface unit. Right now, these files usually use the .ixx extension, which honestly looks kind of weird. You give the module a name, and then you write this slightly scary looking code. First, you specify that this file is the interface of your module, meaning the part visible to other files. Then you place inside it all entities you want other files to access. Those entities are marked with the export keyword. Otherwise, the code itself looks pretty normal, but we still need to implement the function itself. So we create another file, something like math.cpp for the module implementation. Inside it, we write module math semicolon. This indicates that the file belongs to the implementation of the module, and this implementation gets compiled only once. Inside the module implementation, you can still include traditional headers or import other modules. For example, here I import the standard library module std to use square root functionality. Notice that export is not repeated here. Now, if we move to main.cpp and uncomment this code, we can import std to use cout and import our own math module to use our vector utilities. And the project compiles perfectly fine. That's the basic idea behind modules. But I'll explain them much more deeply in a separate lesson later on. And with that, this very long lesson finally comes to an end. This was an extremely important lesson, and honestly, I'm really happy I managed to reach this point, because very soon I'll be moving to another country where I probably won't have access to my computer for an unknown amount of time. Of course, if you're watching this video far in the future where everything already worked out for me, then you're probably already seeing newer lessons on the channel. But right now, at this exact moment, it honestly makes me pretty sad knowing that I won't be able to spend time recording lessons for a while. I really hope I'll be able to rebuild my life quickly, buy a new computer, and continue recording theoretical lessons for you. Thank you all so much for watching this video and all the previous videos if you've been following the course. Thank you for the likes, the comments, and the subscriptions. I genuinely appreciate it. And honestly, I especially value the comments because they remind me that real people are watching the content, learning something from it, and sharing their thoughts and impressions. That really motivates me. If you'd like to support me financially so I can buy a new computer sooner, you can become a channel member or donate using the links in the description or through YouTube's thanks feature. I'll see you in future lessons. Take care. Goodbye.